the green FET presentation. This is about our load switch. We call them integrated power switches, IPSs. Our brand name for them is green FET, and green FET 3 refers to the third generation of our integrated load switch type products. They're perfect for IoT and mobile products, primarily because they're extremely efficient, they're small size, low cost, and we ship these things in the billions of units. So without further ado, we'll do a quick little review of what we discussed in part 1. A few weeks back, we covered the use cases for when load switches are used and when they're necessary in IoT devices and mobile applications. For example, they're often used to reduce the off leakage current. We use them for pulse powering sub-circuits within your mobile applications to save on active power. They're good for noise isolation and various other kinds of things in terms of the actual circuits. The types of load switches are N-channel, P-channel, and then we have a few specialty load switches for, that offer features like reverse blocking, current monitoring, and then a host of other kinds of controls for fast turn on, slow turn on, discharge, and all that other kinds of things. In part 1, we finished off by talking about basic load switch architecture. What are the key components of a load switch? How do they work? Why are they important? Etc. Today, in part 2, we're going to go over how load switches are actually constructed. What makes up the process? Why was Silego revolutionary in how we designed our load switches? Why did we take the market by storm? And then next thing we're going to talk about is switch safety. And this is a major issue in our industry, and you'll see why. We have a lot of great video to show you today about why safety is important in the load switch market. Now, I encourage each one of you to go up to the Silego website, and we've got some great product selector guides in our green FET product families, and they break down roughly into single N channels, single P channels, dual N channels, dual P channels, and reverse blocking, as well as we even have a programmable load switch up there with NVM programmable rise times and current monitoring and this type of thing as well. And so I encourage each one of you to take a look at that, because we'll be referring to a couple of these products throughout the presentation. Now, really basically, why did Silego cause a revolution in power switching? And the answer is quite simply size and cost. If you kind of looked at a power switch that you would have purchased back in, let's say, 2008, 2009 timeframe, you would have purchased a MOSFET that was nearly 30 square millimeters, 6 by 5. This is an actual example. You can go up to DigiKey and you can kind of see these types of MOSFETs that are still being sold today. Silego designed a process, we call it our copper FET process, by which you could take that same basic MOSFET, and here that other one was 10 amps because that's what I pulled off, and ours is 9, not very materially different. There's a 7.5 or 7.8. But look at the size difference. It's 10 times smaller. Now let that sink in for a moment when you're trying to think about mobile applications and IoT applications. It's a massive size savings. Furthermore, because it's so small, it's actually quite a cost savings. The type of device you see on the left here, that thing will cost you 20 cents, 15 cents in major high volume. Our chip is going to be cheaper than that by quite a lot. I mean, not 5% cheaper, you know, we're talking 10, 20, 30% cheaper than these much larger chips that were being sold even 5, 6 years ago in high volume. Now, in fact, the technology got so good that some people just can't really believe how low of impedance you can get within a single tiny little device like that. Our copper FET technology, it can even, we've recently advanced it in the last year, where in a single square millimeter of silicon, really tiny, we can have only 4 milliohms of RDS on. It's quite remarkable. Now, let's talk about power density. One of the nice things about really big parts like you see here on the left is they have 10 times less power density than a device that's 10 times smaller. Now, when you think power density, why is gasoline flammable? Well, the reason why is because it has a very high power density. That's the whole concept of packing a lot of energy into a small space. That's what makes your engine run and things like that. However, you have to be very careful when you take all this power on your board and you funnel it through a little tiny power switch. If you don't have safety circuits and you don't have thermal protection, short circuit protection, a lot of nasty things can happen. And I'll let you watch a video of exactly what that looks like. Here's a particular chip. This is an actual one that is in production today by one of our competitors. In order to save money, they haven't put in the safety circuits. That's how they can remain competitive with our copper FET process, because our process is so efficient that we have a lot of room left over to make sure we can do thermal monitoring, short circuit protection, current limiting, and all these types of things to make sure that when you put so much power through a little tiny device, you don't have this kind of effect. And if you'll actually hear the engineers, they were actually pretty surprised by this. So listen to this. And here's the slow motion. I hope that illustrates to you the importance of what we're talking about. It's one thing to try to get things to be as small as possible, but if you don't take care of the safety concerns that can result here, you can actually get flame. And what we showed you there was a load switch, once again, with no safety protection, no circuit protection, and all we did was we had the output shorted and we turned on the power and bam, the thing flamed. This is not an appropriate product to ship to customers, and yet it ships in volume today out in the market completely inappropriately. Now, there are lots and lots of good answers. Silego shipped, like I said, over 1 billion parts with safety circuits that don't have this behavior and won't do this kind of thing. If you hooked up a Silego chip, and we have hundreds and hundreds and hundreds of them performing the exact same test, it's really boring and the device just sits there and does nothing. That's why our engineers were so shocked to see the device delaminate and flame. Now, let's talk about some of the advantages, because when you reduce the MOSFET in size and you build it on a CMOS process, you can add a lot of control circuits. Some of those control circuits we add are things that allow us to put in a lot of protection. For example, we can put under voltage protection, over voltage protection. We can put various current limiting schemes. We can put short circuit protection, thermal shutdown, auto restarts, reverse current block, all these kinds of different things to make a device both safe and work within your system appropriately. And we'll talk more about that as the presentation goes on. So we're going to explain our copper FET process in a little bit of detail here over the next couple of slides. There were some, but before we do that, I have to introduce you to some really, really basic concepts in terms of the things that changed in MOSFET design that enabled this technology to move forward. The first one is, and you can see it in the upper left-hand corner here, is old MOSFETs used to have the current flow through the silicon vertically. The drain was on top, the source was on bottom, and the current flowed right through the wafer, so to speak. And that was how you built the MOSFET. And it's one of the reasons why, because the channel length is so long here, that MOSFETs were as large as they were. Instead, we went to a standard CMOS process where we built little tiny MOSFETs and we hooked them all up in parallel, and we made them in a what we would call planar MOSFETs, or they're horizontal across the surface of the wafer. This allowed us to reduce the RDS(on) of the overall chip and allowed us to make much, much smaller power MOSFETs. So when you're really buying one of our load switches, you're not buying a single MOSFET, you're buying hundreds of thousands of MOSFETs hooked up in parallel in a planar manner, as opposed to the old style of MOSFETs where the current goes through the silicon. The next thing is, we don't build our MOSFETs on those old large silicon processes. One of the ways that MOSFET manufacturers kept their prices down is after a fab was fully depreciated and no longer was it anywhere near the most advanced nodes in our industry. In fact, it, a decade later, maybe even 2 decades later, would turn them into MOSFET manufacturing plants to crank out these old types of products. That's not what Silego's doing at all. We're actually in 0.18 micron or smaller CMOS processes because this technology requires it. Furthermore, when we integrate all of the control circuitry for the MOSFET, we want that control circuitry to be small. So while we're not at necessarily the leading edge, we're certainly not at the lagging edge of CMOS processes anymore. The third big function that we've done here is we've switched from aluminum to copper, and we just haven't switched a little bit. We switched from aluminum layers to copper layers. We switched from aluminum and tungsten and all the different types of interconnect, and we switched to copper interconnect. The lead frames traditionally have always been predominantly copper, but essentially from the time that electron enters the drain and flows through to the source, everything that it's exposed to, at least on the metal side, is copper. Copper, once again, is a great material. As you well know, if you looked at any kind of power line and cut it in half, what do you see? You see copper, because copper has much better resistivity parameters than aluminum does. Copper is also extremely good at spreading out the heat, and this is going to be a big deal that I'll explain here in the next slide. One of the problems with the old devices is that heat buildup occurred around pinch points within these lateral MOSFETs, such that your product was limited by the current density that would occur in certain areas, because you get hot spots on the die, and those hot spots would be the limiting factor in how you rated your overall device. With copper, we're able to spread that heat out very nicely. And in a kind of a day-to-day analogous fashion, you'll notice that your best cookware in your house has a copper bottom. Why? Because the copper, once again, spreads the heat out a lot more evenly. And then finally, the old MOSFETs, all the MOSFET control was external, but because we build them on advanced CMOS processes, we can integrate the power control directly on chip, as well as all the safety circuits. So instead of having to do level shifters, we've got logical on-off levels. We have soft start, soft on, discharge circuits, current measurement, power good, safety circuits. All these kinds of things can be integrated into our power MOSFET process, which we call the copper FET process. Now, one of the big changes we did was in the MOSFET connections. It turned out that once we developed a very, very low RDS(on) power MOSFET in a lateral sense directly on the surface of our silicon, we wound up with this very, very low RDS(on) MOSFET. But the problem is our interconnect, and you can see it, the style that we first used here was on our right. We basically put a whole bunch of bond wires down, and laughably on our very first products, they were actually gold bond wires. And the bond wires themselves had as much resistance as the actual silicon MOSFET did. Well, as we were putting all these gold wires down and gold started to hit, $1,800 an ounce back in the day, that became a very expensive proposition and far too expensive for, the consumer market. And once again, people were willing to put up with the larger sizes for the less cost, and that wasn't working. So what we did was we had to flip over and use copper bond wires. Now the problem with copper bond wires was copper is quite a bit harder than gold. And so as we were sticking the copper wires onto the surface of the silicon, if you tried to make your manufacturing process go very fast, those copper wires would come and they would hit into the surface of the silicon. And if you wanted to go real fast, you would end up with cracking because you just couldn't squeeze the copper down onto the surface of the silicon quick enough, and you had to slow down your processes. And so we would find that our manufacturing lines were going 3 and 4 times slower than what they were really cost effectively designed to do. So that didn't work out. Now, in the old style way, and you see that on the left here, this is kind of like a standard old style MOSFET where they actually have a clip that they actually can put down onto the surface of the MOSFET, and this works pretty well for those old huge MOSFETs. But we didn't have a comparable technology to use in the lateral MOSFET world. We couldn't put a plate on the bottom of the MOSFET, as you see here, and then a clip on the top to connect the source and the drain. So we had to come up with something different in order to make this work. So the bond wires were too high RDS(on), the copper was too slow, the gold was too expensive, and we couldn't use clips like the old style MOSFET families did. So we came up with this pillar technology, and you'll see that on the next slide, where we were able to connect to the lead frame with pillars. Now, let's take a look at the process now all stuck together. I've indicated what the fundamental components of the technology were, but now let's step by step take you through and explain how it all kind of fits together. So you'll see the actual little MOSFETs down here. These are these little octagonal shaped electrodes down here, and the gate is there, and so the channel is between the source right here and the external, which would be the drain outside of here, and so the channel would be under this green area, or you can see the cutaway here would be green. That channel length kind of sets up the overall resistance of that individual MOSFET, and then you take them and parallelize them out to, let's say 100,000 of these little cells, and you'll get a 20 milliohm RDS(on) overall power MOSFET, if you want to look at it in an aggregated sense. If you want to go to 10 milliohms, well, you'll use 200,000. If you want to go to 5, you'll use 400,000 of these FET cells, so to speak. Now, once you have the FET cells, you got to hook them up in parallel. So what you do is in the center of every one of those FET cells, we've got a metal interconnect that goes through up all the layers of the CMOS process. And for those of you who have been in the semiconductor industry, you'll know that the interconnect is a lot of times we'll say we have 3 layers of metal or 4 layers of metal, and this is to hook all of the transistors together. So that interconnect will come up through all the layers, between glass and metal, all the way up to our top layer, which is grown copper. And that copper layer is fairly thick, and what it allows it to do is, as soon as those electrons get up to that copper layer has almost no impedance and a very good heat distribution quality, so you don't get any hot spots up there, and the electrons can get out through the source quite easily. On the drain side, we don't actually build a second copper layer. We actually come down and we use all the other layers that are available in aluminum. We stitch all those together with interconnect, and that forms the drain, and then we pop all that up to the top. And in this manner, we can have very low resistance in the drain metal interconnect. We have very low resistance in the channel where the silicon part of it is, where we can switch the switch on and off, and we have very low resistance coming out through the source. This forms what we call our copper FET process. Now, that just forms the overall die, what we actually build in the fab. Now we got to take that die and we have to connect that to the overall lead frame so that our customers can actually mount that on the circuit board. And the way that works is this way. We take our wafer and we actually grow these copper pillars. They're instead of growing or making bond wires, we actually have pillars. And so these are grown cylindrical copper formations that come right off the top of the die. And you'll notice this little white stuff, that's solder in there, and I'll explain that in a minute. So we paste these copper pillars directly on the lead frame. The lead frame's made out of copper here. And then it's heated up, and that solder flows and makes a good connection between the copper pillar and the copper lead frame. And there's a little bit of titanium down there to make sure that that copper pillar sticks onto the copper redistribution layer that is grown onto the surface of our wafer there. And therefore, you get really low impedance of electrons coming through here, coming through the cylindrical interconnect, and right down onto the surface of that copper sheet that goes over the top of our wafer, and then down into the actual MOSFET itself. So in this entire process, we're using copper, and more copper to generate incredibly low RDS(on) load switches. And this is what fundamentally makes Silego's copper MOSFET technology a better technology. All right, any questions about that before we move on to the next part of our presentation? Give you guys a chance to ask anything if you choose to. Okay. All right, moving on. Now, because we build this on a standard CMOS process, we're able to also integrate control circuitry. And in the most basic integrated power switch, like we went over in part 1, you have just a few things. You have the ability to do ramp rate control, logical level shifting, discharge circuits, which make up a couple of transistors and a little resistor to help discharge that when you want it to turn off. We can put all of that into a particular package without any difficulty, saving you enormous board area. Even one of these transistors, in many cases, when we looked at our customer circuits, a single transistor can even be bigger than our entire load switch, including the power switch, including the level translator, including all that. And very often, we will save our customers up to 90% of their board area when they want to go use our integrated power switches. And here's another example of some of the various types of things that we'll do. You can see our safety circuits here that we can put in there. I'll integrate that all seamlessly. Once again, we have, like we talked about in part 1, many different ways to control ramp, slew rates on and off, and current limits with resistors and programmability and current monitoring and power fault detection and all that type of thing. All of this is made possible because we're building these power MOSFETs directly where the control circuitry is itself. Oh, gosh. I don't know where that came from. But at any rate, furthermore, because we put these on the power load switch integrated circuits, we actually can put in dual channels, quad channels. We can do a lot of things like that. And you're going to, over time, you will even see some of our pack types of chips be merged in with our power chips, and for all different types of applications. We do beautiful LED, white LED dimmer switches and power control. You'll see that in some of our pack family, like our 46116, 117. These types of devices, we're going to be launching a 46125, which once again puts a lot more control into these power switches. In this case, we'll talk about reverse blocking. Basically, we can put two power switches together so that when the body diode isn't pointed in the right direction, we'll have another MOSFET in there to block that, so that if the voltage is higher on V out than V in, no problem whatsoever. You won't get current flowing back. Normally, if you use a single power MOSFET that you would buy discretely, this will actually double the size of your circuit. But in our case, once again, our chips are so small you'll barely notice the difference in terms of size. Now, we got another video to show you guys today. And this one, once again, I'll title it Safety First. Now we're going to show you a bunch of 5, 12, well, I think one 12-volt device, but the rest of them will be 5-volt devices where, once again, simple shorts, watch what happens to these devices. And I'm going to get out of this and get into my QuickTime here and go ahead and play this for you. Now, kind of, we souped it up. The audio isn't real, but we just thought it'd be a little fun to add that for a little entertainment. But there's nothing funny about people's load switches blowing up into really standard types of use cases where they just get simple shorts. And we'll talk about how these shorts can happen in a moment. You notice how long this one goes. My goodness. There's a product recall. And if you take a look at the Silego devices and you perform the exact same test under any of these conditions that we mentioned here, you'll see no smoke. It'll be the world's boringest test, and we've tested them this way. And it'll just sit there and do nothing, and even more so. I'll give you an actual story that happened. There was we can't mention the customer name, but this customer had designed our load switches into a fairly large box, electronic box. And this electronic box had a fuse requirement as part of their product definition. And so they were required by safety standards to go ensure that they've designed the fusing correctly and that it would protect against any kind of short. And indeed, that's exactly what they went out and did. And they tried to test to see if the fuse would burn. One of our little load switches noticed the short circuit problem that they had introduced into their circuit and promptly shut off, and did it so quickly that it protected the fuse. Once again, we're not advocating, and we don't sell these things as fuse protectors or even fuses themselves, electronic or otherwise. But nonetheless, it all goes to show how safe our products are. And the customer was quite amazed and called us up and said, "Hey, do you realize your devices did a pretty damn good job of protecting against short circuits?" And of course, we knew that, but it was always nice to hear. We put a lot of effort into making sure that. So once again, let's take a look at this. You can't ever watch these things enough. You get really nice little mushroom clouds coming off your boards. So one use case where this matters is, for example, even in your manufacturing line, it's not uncommon to have solder bridging occur. But why have a whole bunch of chips go bad and boards destroyed simply because your manufacturing line had a few hairline solder bridges happen? It's so much nicer to have the load switch protect that area of the circuit. Your team comes in a little bit later, figure out what the problem is, resolves it, and saves your board area. On the other hand, all shorts can happen for all different types of reasons. When I was doing board level design, it wasn't uncommon after a year or two for a capacitor, for example, an aluminum electrolytic capacitor, to go bad and internally short out. That's bad enough as it is, let alone having your load switches that feed that particular power rail smoking as well and starting to create a fire hazard in those lines. And these are kinds of things that I've seen in my own life. This isn't anecdotal. This is things that I've watched, I've seen, I've had to repair working in the labs. So let's go back to our presentation now and continue. The old devices, if you wanted to use the power MOSFETs that were 10 times bigger, they generally didn't have these problems nearly as bad. Obviously, if you went up and used them at hundreds of amps and things like that, yes, they would have the same problems that you see here. And you would have to design in the safety circuit discreetly with some of those very large MOSFETs. But for MOSFETs that were running under the 12, and running a watt or two through them when they short circuited, generally they were large enough, the power density was not so great that they would, maybe they'd crack, maybe you'd smell a little something, but you generally didn't have a fire hazard. But if these little guys aren't designed right and highly efficient, you don't put the safety circuit in there. Be careful what you design in. So now we're going to talk about how this really actually looks in the system. Here's a scope shot of a load switch doing what a load switch should. You turn it on, it runs, the V out goes high, maintains high until you turn it off, and it goes off, it discharges. The load current comes up, the load turns on, the current goes high, and it stops when you turn it off. That's the load switch acting normally, and that's a good thing. And this one, we're just showing it at an amp. Nothing's triggered, no problems whatsoever. However, let's say that your load switch is set up to have a current limit condition and you've overcurrented it, for whatever reason. Perhaps you started up a motor that motor wanted to have 3 amps or 5 amps, and your power supply system is not able to supply that, but your load switch, it's already on, is so low that it could easily pass that kind of current unless we design in the circuits to say, hey, don't pass that. So in this case, what will happen is you're passing too much current. You want to limit that current. The load switch goes into current limit. Because it's so small, as it starts to current limit, the RDS on spikes high, because the way you current limit is by switching the MOSFET partially off. The RDS on spikes up. You have to start dissipating a lot of power inside that load switch, which makes the thermal temperature of that load switch start to rise very, very rapidly and immediately go into an unsafe condition, whereupon our thermal sensor will detect that and completely shut the MOSFET off, which completely shuts the power off. And you'll see that as an automatic shutdown of the load switch to protect itself. Now, as soon as the load switch is shut off, the current's shut off, there's no more power dissipation, the die will start to cool. Now, generally, it depends on the particular part you buy. Some of our larger parts, they'll go up to 140 degrees C, 150 degrees C safely. The vast majority of them we cut off at around 125 degrees C internally inside the device. And then we force a cooling down, in many cases, down to 100 degrees C. Some of our programmable ones will go down, all the way to 85 C. Whatever is necessary to have a large enough hysteresis between the top thermal and generally about a 25-degree step down to before we turn them on again. So it depends on the product you buy, but nonetheless, we have a thermal hysteresis anywhere on the low side of probably about 25 degrees C, and on the high side, programmably of maybe 50 degrees C. And then the devices can automatically turn themselves off. If the current limit condition still is there, the device will shut off again and come back on, and if it's still there, and it can repeat. Some of our devices have fault power pins, and when this condition happens, the fault signal will go high, and if you have a microcontroller or one of our pack chips can detect that fault protection and go, okay, after 3 faults, let's not restart this thing anymore. Let's just leave it off. Maybe you want, after 1 fault, it stays off. Maybe you don't ever want to recycle it. Once it goes off, you want to just maintain it off, so you turn off the enable pin on the load switch. You go try to figure out where that short came from or force the user to do a manual reset. There's all different types of ways that various systems are designed to respond to various faults. But if you just leave it on, this thing will continue to power cycle, always keeping the load switch in a safe operating range and trying to maintain the thermals on the device so that you don't run into further problems and the thing doesn't go into spontaneous combustion as you saw some of our competitive parts do. And believe it or not, when you get into these small devices, the safety circuits can take up to a quarter or even a third of the area of the die. So it is a monetary issue. When those circuits are not put into the die, it's simply to save money or to provide a higher performance for that particular spec. So be very careful. If you're a designer and you don't care about safety circuits, be forewarned. Think about what you're doing. If you can guarantee that you current limit somewhere else in the device, okay. But make sure when you design anything, if you're not going to put those safety circuits in, make sure that you don't have any kind of conditions where you can get thermal runaway, or you can get conditions where you get inadvertent shorts and you create yourself a hazardous condition when you're using these very advanced parts. Now there's a number of different types of short circuits. One is a short circuit that happens while your chip is active. That's what we just looked at. Another type of short circuit you can have is a short that's already existing, and there's a gazillion reasons why these can happen, from tin whiskers to other parts going bad to manufacturing defects to batteries aging, all different types of reasons why shorts can occur while everything is off. Once those shorts occur and that load switch is asked to be turned on, most of our load switches are designed with safety circuits that can detect, oh, you asked for this load switch to be turned on. We started to turn it on, but the voltage wasn't coming up. It looks like you've got a short. And if that short during the ramp goes over a particular current rating, once again, depending on the type of product that you're buying from us, but let's say in this case, 250 milliamps, if you just start to turn on that V out and you immediately start to see, oh, I've got 250 milliamps flowing when I don't really expect that to happen, we can leave that product off and never continue the turn on of that chip. In the cases where the device also has a power fault, the power fault will go high, and then you could try to take care of this problem with wherever it exists. But this is a way to protect your circuits and not cause fire hazards and all the other kinds of things that go on if the short is already existing when before the load switch is active, asked to be turned on. So we have those two types of, fundamentally, those two types of safety circuits. One, a safety circuit when things are active, safety when shorts occur when the power is not on, and then of course we always have thermal protection existing and making sure that the design is always maintained within a particular temperature rating to avoid thermal runaway problems. Now let me describe exactly what thermal runaway is. As the temperature increases on the MOSFET, the MOSFET impedance actually goes higher. And as the impedance goes higher, the power dissipation gets greater within that MOSFET. This causes even more heat to be generated. And so even though it, you know, on the back of the napkin, you might think, oh, I can run under a fault condition for so many milliseconds before I've got a problem. You better think about your RDS on might not be linear. If you start to go into a fault condition and that die heats up, you can have conditions where the RDS on jumps up 30 or 40% over what you might expect. So if you're going to do your calculations on that and running without safety circuits, you better add about another 30 to 40% in your calculations in order to compute for that. In our case, we've got a temperature sensor there, and that will handle it. If you're above a particular temperature, you're good to go. This thing will, our chips will automatically handle those kind of problems for you. Now, as we kind of start to wind down in our presentation here, be advised we have the product selector guides on our website for both our low voltage GFET3 products and our high voltage HFET1 type of products. You'll see that all of those are there. They're very easily to go through. We have a lot of application notes on the proper way to lay out load switches and whatnot. The layout of load switches is very important because we spend a lot of time and effort to make sure that we use copper for heat dissipation and things like that. Well, it'd be real sad if your layout uses thin little traces that come over there that have their own RDS(on) in them. And so once again, please read the application notes on the proper layout of our load switches. If that fails, go ahead. We have an excellent FAE team led by Chuck Husted that can provide all kinds of technical support and are very, very familiar with the proper use of load switches and proper ways to lay them out, all that type of thing. What to watch out for, how to avoid inrush currents, all these kinds of things. Our FAEs are phenomenal, and we've got them placed around the globe for you to make use of, as well as our sales teams. They're very, very aware of that. So I'd like to spend a few minutes, if any of you have any technical questions or about our load switches or safety circuits, or want to watch our videos again or anything like that, feel free to ask any questions now. We can answer them. So one person asked a great question. Does the reverse blocking continue to work if the input voltage is removed? The answer, the direct answer to that is it depends. In some cases, our VDD is still active on our parts, and all the biasing it maintains where it needs to be, in which case the answer is yes. However, if the VDD is taken from our particular chip, you have to be very careful in some of those situations. In some of the situations, the answer is yes, and in other situations, you will have a little bit of leakage, not a lot, but you'll have a little bit of leakage continuing on in the device. Another question was asked, how does Silego parts differentiate themselves from competitor parts like TI load switches? That's a really good question. The predominant way that we've differentiated ourselves is Silego's absolutely shipped billions and billions of our parts into our particular customers. Our safety circuits are second to none. We provide a high level of customer support in terms of characterization data. We have SPICE models on all of these kinds of things. And we, once again, we try to make sure that our parts are among the safest in the industry. Is there any other questions that people would have? Can you, another person asked a follow-up on the reverse line. Can you bootstrap the output to the charge pump? We do it well, there's two types of our, if you would have been on the part one of our presentation, we kind of described exactly how the reverse blocking was going to go. But essentially, depending on which style of load switch we have in-channel load switches, in which case there's internal charge pumps that actually pump up, and it's one of the beautiful things about the load switches is it's a regulated charge pump. So when you have our N-channel load switches, that charge pump is regulated at roughly 5 volts. It varies depending on the particular type of load switch, but roughly 5 volts above the drain. And what that allows is it allows a constant RDS on. So even if the input voltage is varying around a little bit, let's say you're hooked up to a lithium-ion battery or something like that, the RDS on of our load switch will be constant throughout the entire discharge cycle of that of the battery, for example. And so all of that bootstrapping, so to speak, is handled automatically by our load switches. That was a good question. Okay, I'm not seeing any other questions. Thank you all so much for attending our seminar part 2 on IoT and mobile load switching. And once again, thank you so much. Take care. Bye.